like to share my screen and give you a background of how SoFSI started, because I understand that you already did the tour and you know the end of the journey. So I'd like to share with you some challenges in terms of construction and how this facility was actually built at Langford campus. After obviously acknowledging also the contribution of my collaborators, I see Vlad and Rafael, obviously, Colin Taylor, Adam Crew, George Milonakis, Dimitris Karamitros, and other quality people. And of course, the contribution of Patrick and David and Tony that work on site. So sharing my screen, let me just show you a couple of number of slides, which basically summarize this journey, as I mentioned, as this really leads us the history of experimental electrical engineering at the University of Bristol. I don't know how many people you can recognize going to this legacy of 1987. Definitely, we can recognize late Professor Severn, had the vision to set up this very first shaking table, and Professor Colin Taylor, who was the pioneer in setting up all the rest that you're gonna see. So this was the first initiative years ago to study earthquake engineering and structural dynamics at the University of Bristol. Then in 2005, the plate earthquake table was introduced. Had the honor to have the presence of Her Majesty the Queen, which very sadly passed away, as you know, recently. In any case, this was a very important event because it introduced new capabilities for the University of Bristol. I'll tell a few things more about this in the future, but this is what we call the existing lab, the blade or the equals lab in Queen's Building in the main campus. And it basically refers to a 6 degrees of freedom 3x3 platform that is operated with 8 dynamic hydraulic actuators. It can bear a payload of 15 tons, but let us say that for performance, it's basically around 10 tons, which is pretty good actually for 6 degrees of freedom. Up to 2G acceleration and a stroke plus minus 15 centimeters. So there have been many tests all these years on the equal shaking table. Now, a few years ago, like 7 years ago, there was this initiative at the national level called UKCRIC, which probably you're aware. This is a huge investment of 138 million on 13 facilities and 6 observatories to deliver high-quality research infrastructure in the UK. These world-class facilities were developed in several universities, as I said, Bristol being one of them. Bristol received about £12 million to deliver what you just saw. And this is quite a fantastic opportunity for all universities. I take the opportunity to also inform you that now UKCRIC is evolving. It's not a closed club. Universities and entities can aim to become affiliate members at some point. So please stay tuned, because this is an ecosystem of R&D that is quite open and will change and be very inclusive in the years to come. Now, SoFSI came therefore with a basic idea of a very large shaking table, dynamic and a dynamic shear stack and 12 million in hand to deliver what you saw. But obviously, the final product, the final structure, configuration, infrastructure was the result of a very long process of interaction with many different entities. Because there were several challenges that had to be faced, starting obviously from the location of construction, which was not given when we started. And therefore, while waiting for the site to be allocated, we were trying to, cultivate the relationships with industry in order to produce something that is not just innovative from a research point of view, but it's also useful for the industry and the society as a whole. Langford campus, obviously you're aware because you're there. Therefore, there's nothing more to say on this other than highlighting the footprint of the courtyard and the building, and just presenting some of the collaborators. Many of them are part of the Industrial Advisory Board. This has been extremely useful, as I mentioned, to contextualize the operation and the design of SoFSI. SoFSI, you already observed that as three main entities, the pit, the table, and the hexapod, which we're going to discuss a little bit more in the future, but this is how it looked like at the beginning. You don't even see right now the entire reaction mass that was laid on, casted on site to make sure that the whole thing is, its foundation is robust and stable. It was a very challenging project also because it was delivered in the middle of the pandemic with all the challenges that you can imagine. Right below, there is a city of, or and let us say, a network of pipes, trenches, the main hydraulic ring, where the power and the oil flow are distributed to all the actuators that are needed to operate the two tables and the soil pit, including also the data acquisition cabling. So that's about 30 meters of infrastructure at a layer right below and within the reaction mass. Probably you entered already the pump room, and David, Patrick explained to you what's all about, so I guess I don't have to explain much about this. And you can also see that three entities, as they were designed, basically aim to be complementary and deliver different capabilities for Bristol and its collaborators. For example, to start with the table, that's a 50-ton payload, 3 degrees of freedom, two translational and 1 rotational, and it's able to meet the Bell curve. Don't know if David had the chance to discuss about this, but this is a very, very demanding care for spectral matching when generating the motions that are running. They're using to run the table. This, in terms of amplitude and frequency content, meet this very demanding protocol, similar to what IEEE is producing for seismic qualification of important equipment. And this goes up to the performance of the table, up to acceleration of 2G and a maximum frequency of 50 Hertz. So this is really a very powerful table, 6 by 4 meters. You can also see how challenging it was to kind of accept the delivery of the table, the construction of the table initially during the pandemic through Zoom, I would say, which is quite a challenge. And also you see the time lapse of construction starting from the bare ground, excavation, reaction mass, and gradually how the whole shed was constructed. Now, from a civil engineering point of view, maybe you could say that the superstructure is pretty simple. It's a steel structure, which is pretty much true. But at the same time, you have to recall that this 12 million covered both the equipment and the construction of the building and the reaction mass. And this is depending on the interplay in terms of cost and performance of all the things that were designed within the laboratory, which means that the SoFSI had to be novel. It had to be kept within the budget, within the time frame. There was a very challenging limitation that all the funds that were not spent at the end of the financial year were lost. So all these risks required very careful design and costing of the overall initiative. And this also meant that during the pandemic, this was exceptionally problematic and difficult. Overall, however, I think we delivered the whole project at a quite decent state. We delivered everything that we envisioned initially. Probably the shed is a little bit, it's one day smaller than the initial design due to recoding and redesigning of the facility. And the pit was supposed to be a little bit deeper. Now it goes down to 4 meters. But overall, all the major infrastructure that we planned to deliver are there, as you've seen. So what can we do in SoFSI? In SoFSI, we can basically run large-scale experiments on structural dynamics and geotechnical engineering, study problems where structures interact with the soil, because after all, this is a soil structure interaction facility at the national level, but also offer the possibility for multi-scale, meaning we can do small-scale testing in our geo lab, for instance, let's say a little bit larger testing in the equals lab, even larger testing in SoFSI, and probably prototype scale in the field. So this is multi-scale earthquake engineering for basic infrastructure, including also nuclear engineering. We can also deal with multiple hazards because this is essentially a facility that applies dynamic loads, and dynamic loads can be seismic loads, but they can equally be wind loads. Flood is more difficult to reproduce, though not entirely impossible into the pit. But let us say wind and quake are perfectly feasible, plus other types of dynamic loads. And then it's not just infrastructure, it is also what you're testing on the table or within the pit, like smart materials, like components of energy infrastructure, like pipelines, wind turbines, railways that interact with soil, bridge abutments, retaining walls, structural components, very strange 3D printed or whatever types of new materials, retrofitting techniques, and all the like. And of course, given the extensive instrumentation that we can implement, this can generate very detailed benchmark cases of well-controlled experiments in an environment that we measure exactly what's happening in terms of input and output, loading and response, which produces or is able to produce quality data sets that are actually missing from a series of complicated systems. So this is pretty much, let's say, the main things that we can deliver within the lab. Obviously, you've seen the table, but this is how the platform was installed. The platform itself is 30 tones, so it's quite challenging just to break it in, given that the capacity of the frame is 30 tones. I suppose you already had a demonstration of the table, so I'm going to skip the video, because I reckon that you've seen it already in action. And also,
can you play the video, because the table's not running because the hexapod's being installed, so it would be helpful.
Okay. Fair enough. Thanks very much, Patrick. Here you are. This should be El Centro earthquake, which was, as you know, the first accelerogram ever recorded, and without any additional scaling. And it was obvious that the motion was primarily dimensional. As I said, yaw can also be implemented, rotation around the vertical axis. Now, another thing that you may have a chance to notice, or maybe not, because there are many things happening in the lab, is what you see on the right-hand side. This is the shear stack. By using the shear stack, which is like 4 meters long, 1.5 and 1.2 in the other two directions, this is a box, a dynamic, flexible box, which is normally filled with soil, and this is placed on the shaking table, and we're running tests that include the wave propagation from the base, let's say the bedrock, up to the surface, including in scale whatever buried infrastructure or a superstructure that we can have in mind. So this goes and has been used extensively with the other shaking table in Queen's Building, and it will also be used actually in SoFSI as well. Another view of the facility when it was cleaned and when it was not occupied by sound and other things. But obviously, the busier the lab and the dirtier the lab, the better, in a sense. It shows that things are done. One important thing that I don't know if David had the chance to discuss with you is how the shaking table is controlled. Because one thing that we need to bear in mind that this is a hydraulic system, which means that the motion that we're aiming to apply is not exactly the motion that is actually applied on the table due to damping and other viscous phenomena. Therefore, there is a need for dynamic control and correction of the motion of the table in real time. Therefore, there is control of the motion that is aimed to be applied, but then, as you see, there's a series of sensors, displacement, acceleration sensors on the table that measure the performance of the table and then make the necessary corrections through an iterative algorithm, so that the actual motion that it is applied is not exactly what we would like to apply, but the outcome is exactly what we were aiming for. So this correction is typical for controlling shaking tables, but this is something important to know that requires some background in structural dynamics and structural control in handling this quite delicate pieces of equipment. Same applies to the hexapod, which was under construction, as you know, this week. This is kind of a different shaking table because it goes up to 10G. It has 6 actuators, not 8. And the benefit is that they are eccentrically connected, which makes the control of the table a little bit more complicated, but it is very efficient, and it can produce, as I said, very high accelerations, very high frequencies, up to 50 hertz or more. And therefore, this creates a series of opportunities for testing small specimens under very extreme dynamic loads. We already use that extensively for seismic qualification. You see here the design of the platform and many other details that I can come later on. And also an example of the convergence of the iteration process for the reasons I explained previously in terms of achieving the exact motion that we're aiming for. In terms of instrumentation, I'm sure that you didn't see much because it's not installed yet, but you can envisage something in the new lab similar to what we have in the existing lab, which is basically a set of accelerometers and three-dimensional displacement infrared markers, an infrastructure like the steel frame that you see here equipped with infrared cameras, which are able to follow the motion of like 2,600 markers or points in real time at a resolution of 0.1 millimeters. Therefore, with this information, we can actually then reproduce a digital twin and the movement of the specimen in space, which is really key for dynamic testing. The soil pit, obviously, it's not entirely empty right now. This is how it was designed. Forces are applied through the trench. Most probably, you have already seen that. And this gives us the opportunity to use one of the three actuators. We've got two static and one dynamic, 1 meganewton capacity, and half a meter stroke for the dynamic one and 1 meter stroke for the pseudostatic ones. And this gives us the opportunity to apply lateral loads either at the level of the trench or at the level of the ground floor on the whatever we're testing within the pit. Let us say the abutment, integral bridge abutment that we were testing. And I hope that Flavia Rafaela, who has been leading this effort, told you a few things about this test. This is the dynamic integrator before being assembled in space. Actually, that was the static one, I'm sorry. And this is pretty much what was tested before the whole thing was dismantled the previous month. You can see here, this was the flap that was hinged at the base so that it was pushed laterally by the static actuator slowly and gradually so that the pressure behind the wall and the reduced stiffness within the soil profile was able to be measured by different means of instrumentation. So this gives us really great opportunities. That was a pilot test. Next test most probably will fill the pit entirely. It's going to be dynamic. And, you know, the sky's the limit. What one can do here. But this involves filling the sound, emptying the sound, compacting the sound, and the like. You should also, in a brainstorming sense, consider anything that relates to energy, probably. An example of an offshore wind turbine and how this interacts with the structure, how its frequencies evolve in time because of cyclic fatigue or other phenomena that take some time to develop, and this can all be tested in the lab. We can test abundance of pile groups by creating a reconfigurable reaction frame on top and then applying the forces top to bottom, like forces and moments. As you see here, to static kinematic pile group interaction. We can test train railway soil interaction in a dynamic sense, which is also something very useful to do. That's not necessarily earthquake engineering, as I said. And we are also setting up our own instrumentation system and our own digital twin to be able to measure ground motions within the accelerations within the laboratory and beyond. So I try to give you an overview of how we started from scratch and where we actually ended up. I'm very happy to take any questions. The purpose was just to tell you that something starts, the vision, in this case it was Colin's vision, to apply for something like this. Then it was designed, procurement and tender followed, it was constructed, it had to be redesigned a couple of times, it was handed over, we had to validate and accept all the equipment, do structural monitoring, and ultimately now we are running this facility, hoping that we'll have the chance and the pleasure to work with you collectively or individually as you see it. Thank you once more for visiting our new laboratory, and we're always at your disposal for anything further. Thanks.